You can start, yeah.
So thank you very much, Ian. Good morning, ladies and gentlemen. It's a huge pleasure this morning to introduce our first plenary speaker, Professor Melina Freitag. So Professor Freitag did her first degree in Chemnitz before moving to England, where she did her PhD in Bath, and she then held a GWR Met Office Fellowship in Bath before becoming lecturer and senior lecturer in Bath. And then, unfortunately for England, in 2019, she was appointed as a Professor of Data Assimilation in Potsdam, which is the position that she holds now. Professor Freitag has a wide range of interests in computational mathematics, including neural computing, inverse problems, imaging problems, Helmholtz equations, problems involving bifurcations, all of these underpinned by her interest in numerical linear algebra. And in fact, for the last 2 years, she's been the chair of the SIAM activity group on linear algebra. She's one of the members of the managing board of ILAS, and it's a pleasure to invite her today to give her talk on solving parametric eigenvalue problems by Taylor series and Chebyshev expansions. Melina. Thank you.
Right, so that should work, hopefully. Switch on my microphone. Thank you very much, Marco, for this very kind introduction, and also Marco and Ian and the organizing committee for inviting me here. It's a pleasure to be here. It's a pleasure to be back in the UK. I always love coming back to this country. I miss it a lot. I always say I moved from one pretty city, Bath, to another pretty city, which is Potsdam, but still, anyway. So I'm glad to be here. I'm a little bit of an outsider to iVoter, I would call myself, so I'm not working on operator theory. I'm a numerical analyst, as Marco has mentioned, so I'm very much numerical analyst rather than an operator theory. So I'm a learner at this conference, but actually I'm a learner at every conference. So I'm excited to be here. So this work is joined with my postdoc, Thomas Mach, who has usually did most of the work. And we've been doing this over the last 1 or 2 years. I also have to say, I have just been back from maternity leave on Monday, so this is my first full week at work. Right, so a good way to start. I'm going to motivate why we're trying to solve parametric eigenvalue problems. So I've worked a lot on eigenvalue problems, but so parametric eigenvalue problems is sort of a new thing for me. At least, and I want to motivate where this comes from for us. So I have a sort of motivating example. We want to answer the question: Can one hear the depth of the water? And this is actually inspired by a paper where they ask, can you hear the shape of a drum? So you might be aware of that paper from Mark Kutt. So what we want to do, we have a chain anchored. This is a very simple example, just as a motivation. Anchored below the water on the ground, and it's also anchored above the water. So you have this chain, and you can model this chain as a spring mass system. We have some masses below the water, some above the water. For simplicity, all the masses are the same, set to 1 here, and then we also got some strings above and below the water. And we actually want to know the depth of the water, or if you like, the number of masses below the water. There's some damping going on here as well. We're assuming there's obviously more damping under the water than above the water, and then there's a smooth transition. Yeah, this is how we model it. And then we measure the positions of the masses, and obviously when we move this, we get the positions also make some noise, right? And this is why. So can you hear the depth of the water? Yeah. So obviously just to make the slide title sound good. So we have a discrete dynamical system. So after we discretize, we get this discrete dynamical system of the following form up here. This basically arises if you, for example, model this by stochastic differential equations, because there's also some noise, right? Stochastic differential equation with me, say Brownian motion, and then when you discretize this, you get a noise which is a Gaussian noise, and then you have this matrix A here, which depends on the parameter mu, which is the depth of a water, which you don't know. There's a couple of things that I've essentially said already. We model this by this chain. You've seen this in the picture, where some of the chain is under the water and some is above. And we want to know the depth of a water, which is this parameter mu. Very simple example, very easy to understand. What's said down there I've mentioned already. And we want to estimate this mu knowing only the trajectory. So this is actually something, a very simplified version of what we work on a lot in our CRC on data assimilation. So we have data, and we want to estimate parameter estimation, or a state of a system, which is state estimation. And it's very much an inverse problem, so I know Barbara's here somewhere, saw her coming in over there. So it's very much an inverse problem, but it's a dynamic inverse problem, and dynamic inverse problems are often called data assimilation problem. Well, data assimilation is just a very special kind of inverse problem where we also have time dependence, which is usually or often not the case in inverse problems. Anyway, this is probably the only point I talk about inverse problems. So here's the mechanical model for this particular system. So we model this as a mass string system. So we have a mass matrix, a damping matrix, and a stiffness matrix. Everything is sort of set in a very simple way here because we just want to check if things work, right? So the masses are all 1, as I said. So the mass matrix is the identity matrix. The stiffness matrix is this tridiagonal matrix, and the damping is sort of this is the damping depends on the parameter mu, right? The damping above water, we just set 5, and below water 10, and there's a smooth transition between above water and below water. N is the size of the system, which is the number of masses that we have. Yeah, I is the ith entry of D. D is just a diagonal matrix, and mu is this parameter we'd like to estimate. So relatively simple problem. I know this doesn't model the whole thing properly. To solve this differential equation, you make an ansatz, and then you have to solve an eigenvalue problem. And here it's basically a quadratic eigenvalue problem because we have lambda squared appearing, lambda and identity term here, or a constant term. And it's a special case of a polynomial eigenvalue problem, and we could also look at nonlinear eigenvalue problems. Here it's just quadratic eigenvalue problems, and we actually transfer it to transfer is the wrong word, but we rewrite it as a linear eigenvalue problem because this is what we've looked at so far, only linear eigenvalue problems. So how do we do this? It's just a familiar linearization, hopefully. So we write this problem as a linear eigenvalue problem. Here actually a generalized linear eigenvalue problem, but I put generalized in brackets because our mass matrix is the identity, so this will just be a standard eigenvalue problem, a standard linear eigenvalue problem. We introduce another variable. It's basically what you do when you solve change a second order differential equation into first order differential equation. You get this linear eigenvalue problem. So if you rewrite this again and substitute, you get back to this quadratic eigenvalue problem. So I think that's familiar to this audience. So you have this bigger matrix, which is a 2n by 2n matrix now, and it has the stiffness matrix and the damping matrix as entries. So this would be the standard eigenvalue problems if you didn't have any parameters, right? But we have the damping matrix depends on this parameter mu, and so this matrix depends on mu, and also the eigenvectors and eigenvalues and depend on the parameter mu. Right. For the example that I looked at, how do we go about? So this is just to give it a hint of how we solve this problem. If you want to know a little bit more, we have a little PAM paper which is available. The most important thing is the red thing. We want to compute all the eigenvalues and all the eigenvectors of this parameter-dependent matrix all at once. And this is needed for the algorithm for the solution to the inverse problem, essentially, right? We usually choose a prior mu, and we update this prior by some algorithm. And what we do, we transform this trajectory, which we have, onto the eigenbase. We map it onto the eigenbasis, and for the in order to compute the eigenbasis, we need all the eigenvalues and eigenvectors of the matrix, parameter dependent. So we transform that, and then we do some sort of stationary iteration to update the mu until it converges, and that's the mu that we then use. I don't talk a lot about the noise, so we have to do some regularization as well if the noise becomes too large, so we do some truncated SVD. But this is sort of essentially what we do. What we can also do is some Markov chain Monte Carlo method to estimate mu. So we have a prior, we update the prior, but for that we always need to compute all the eigenvalues and eigenvectors of A of mu, depending on mu. Yeah? And we want to do this ideally very cheaply, so before we actually get into the algorithm, because the algorithm is expensive enough, right? MCMC, Markov chain sampling, it's expensive. So we want to get to the heart of this, which is this problem. Okay, so that's the motivation. Oh, I've already got the plot, so what this looks like in the end. But I'll get to that example later on again. So we know that the eigenvalues, that the parameter is somewhere between 2 and 4 in this example. What we chose to generate this problem was 3.2, and just after one run of the iteration, we get that's the density estimator. The blue line is the kernel density estimator. We get relatively close to the value that we initially put. But I get back to that example later on. So let's get to the heart of a problem, which is estimating, which is computing the parameter-dependent eigenvalue problem. Solving the parameter-dependent eigenvalue problem. So just some introduction. So we have a standard eigenvalue problem everybody knows about. If A depends on the parameter mu, then both the eigenvalues and eigenvectors also depend on mu. So this is what we call the parametric eigenvalue problem. We are not the first people to look at that. We assume A is an n by n matrix. If we fix mu, we can just solve the standard eigenvalue problem. But we want to compute the eigenvalues and eigenvectors for a range of values of mu. If these are just some very straightforward facts. So if A itself is positive definite for all mu, then we call also A of mu positive definite. And what we do assume, there's one more point here. This is not. This is different from these kind of problems. So this is a nonlinear eigenvalue problem, so that's not to be mixed up, right? This is a nonlinear eigenvalue problem where the matrix depends nonlinearly on the lambda, which is the eigenvalue. So that's different from the parametric eigenvalue problem. So lambda are my eigenvalues, mu is the parameter, just not to be mixed up. And it's also different from this eigenvalue problem where the matrix A depends on V, which is the eigenvalue problem, so that's depending non-linearly on the eigenvector. So there's people around Elias Jarlepring in Stockholm, they've worked on these kind of problems. So these are different problems, that's not what we look at. And what I assume is that the entries of the matrix are depending smoothly on mu. So yeah, we're not the first people to look at this problem, so I have a list of names. It's not complete at all, so please don't feel offended if you work on this problem and are not listed, but please do talk to me if you did work on this kind of problem. I have a bit of a slide which says what they did, but only sort of very briefly. So the work by Elman and Susedik, they basically use inverse iteration, but they do a polynomial chaos expansion, so they assume there's an expansion like this. And then they do inverse iteration to find the smallest eigenvalues of this problem. So they are very much interested in stability analysis, so they're only looking at a few eigenvalues. Similar to Ghanem and Ghosh, but they, instead of using inverse iteration, they use a Newton-Raphson method, but it's just a few eigenvalues that they're looking for. The same for Raman. They compute statistical moments of this generalized eigenvalue problem. Again, they compute only a few eigenvalues and eigenvectors. There are a couple of authors that use a finite element discretization for the eigenvalues and eigenvectors. So but again, only for computing a few eigenvalues. So this is sort of in common for all these problems. They only compute a few eigenvalues. So they use some sort of either inverse iteration or a Krylov method to compute a few eigenvalues. We want the whole spectrum. Okay, here's a second example, which is very simple, and we test basically our method on this example. We have principal component analysis of a Gaussian kernel, and we have this sort of Euclidean distance matrix. So U is a matrix which has the Euclidean distances between all the points x1 and xn in our n. So we have got n points, so it's an n by n matrix. The diagonal is obviously 0, and the points are supposed to be disjoint. Obviously U is a symmetric matrix, and the parametric eigenvalue problem we look at is this e to the mu minus mu u, where here e is not the matrix exponential, it's the Hadamard exponential. So we take each of the entries to the power of mu times u, right? And so this is denoted by this 0. Here it's actually written out again. There's a couple of facts for this problem. So it's known that if u is U is almost negative definite. That means the inner product V Hermitian UV is negative for all the V's which are orthogonal to E, and E is the vector of all ones. Yeah, this can be shown. So the earliest references I found was this one. So this is known. It's almost negative definite. So only this vector for this vector, it's in this case 0. So it's not negative definite. And if U is almost negative definite, then it's known that A of mu is positive definite for positive mu. So that can be read up in the Bible of matrix analysis, Horn and Johnson, for example. And if all the points are disjoint, which I'm assuming, then we have positive definiteness. So this is a very simple problem. So A of mu is symmetric, positive definite. So if any algorithm that we find works not well on this problem, it probably fails on everything else, right? It's a very simple problem. Yeah?
There's a little circle under the exponent. Is it entry-wise exponent? Or
yeah, it's entry. This is what it means. It's a sort of Hadamard exponent. So this is entry-wise. Okay. And then, yeah, it comes back to that. If it wasn't entry-wise, the problem would be trivial, because then you can take the logarithm and then just use your standard method and scale. Yeah, so this is not the same as the matrix exponential, just entry-wise. And it's just an example that we look at on top of the example that I think I called this example 4. It's sort of the final example. Can you hear the depth of a water? I look at that, but this is sort of the simplest example you could probably come up with for a parametric eigenvalue problem. Here is just it's probably not important what this looks like, but it generated a couple of equispaced points. N is equal to 8, so any numerical analyst will probably say this is a super tiny problem, right? So an 8 by 8 matrix I generate by using these Euclidean distances here, just from the curve on the torus, and then we get our matrix. We use this Hadamard exponential and get a parameter-dependent matrix. And what we do, just for a sanity check, we because it's a small problem, we can actually compute all the eigenvalues for every parameter mu. So we compute the eigenvalues for a range of parameters between 0 and 0.25. Compute all the eigenvalues, and there's a couple of things to observe. So these are obviously the eigenvalues change as you, so you're on the y-axis, you've got the eigenvalues. There are 8 eigenvalues, you should see 8 curves. What else did I want to say? There's 8 curves. There's a couple of things to observe. The sum of the eigenvalues should be 8. Because the trace, the trace is 8, so the sum of the eigenvalues is 8. So it's always 8. It's 0 for 0 parameter, 1 eigenvalue at 8, all the other values at 0. Kind of works. As you become larger, there are basically 8 eigenvalues at 1, so the sum is also 8. So this kind of works. What you also observe here, there's actually a crossing, an eigenvalue crossing here. If you zoom in, there's an eigenvalue crossing. So there's a couple of interesting things happening which we can check happens with if it works for our algorithm. Right, let's look at the actual algorithm. And we actually have we started with a very simple idea. I said our matrix is smooth in mu. So we thought, okay, we do a Taylor series expansion for A, depending on mu. So we have a Taylor series expansion, A0, first term, second term, etc. Right? You know how a Taylor series expansion works. And we assume we have Taylor series expansions for the eigenvector and the eigenvalue as well. So this is the Taylor series expansion for the eigenvector and the Taylor series expansion for the eigenvalue. Okay, and then what we do, we compare the coefficients. I mean, very simple idea. So we compare the constant coefficient, then we got A0 times V0 is V0 times lambda 0. So you get a standard eigenvalue problem to solve, which you can solve once. Okay. If I assume this normalization, I also get that the eigenvector, the constant, the first eigenvector V0 is normalized at 1. Okay, that's not so exciting. For the second term, if I compare the coefficients, it gets a little bit more calculation. So if you, but it's still not so involved. But so the second term then mixes. I mean, we could just maybe do this together for this one. So you've got A1 times times V0 because it's the term that's a linear term. This is quadratic, so we neglect, we don't use that. And then we've got A1 times V0, which is here. Then we've got A0 times V1, which is here. And then on the right-hand side, we've got V0 times lambda 1. So that's crossed, and V1 times lambda 0. So you get this one. Okay? And I reorder this, so all the terms that I do know and the terms I don't know. So A0 I have. V1 is something I'd like to calculate, but V0 and lambda 0 I have already. A1 is also given. So if I put this together, I should probably put it on the one slide. I have, what I'm looking for in this equation is V1 and lambda 1. Okay, all the other things are given. So I can rewrite this as, oh yeah, and I also got this orthogonality here if I plug the Taylor series expansion in this thing. So if I rewrite this, I get this sort of bordered or block structured system. So I have my standard eigenvalue problem I solve, and for the linear term I get V0. If you look at the first line, V0 times V1 is equal to 0. That's the orthogonality condition. And in the second line, let's just read it out. V0 times lambda 1 plus lambda 0 minus A0 times V1 is A1 times V0. And this is exactly what is written here. Yeah, I just put A0 minus lambda, hang on, I'm getting confused myself. I just put A0 minus lambda 0 times V1 together here, and then I've got this extra term. So if you write this out, you get exactly this ordered system. And you can carry on. So if I didn't write this here because it gets very long, but if I look at the quadratic term and rewrite everything, I get again this matrix I get different values here, which is the coefficients for the second term, and I get a different right-hand side. And if I do the kth term of the Taylor series expansion, I get the same matrix here, so it's always the same matrix. I get the coefficient for the kth term, and I got obviously a more complicated right-hand side, which involves all the previous computed terms. So there's a couple of things to note. The terms on the right-hand side I always know because I computed this standard eigenvalue problem. Then I've got A1 and V0. Then I've computed this. I've got lambda 1 V0, which I can use, lambda 1 V1, which I can use on the right-hand side here. So it's all given. Compute lambda 2 lambda V2, and the same, these terms, I have to compute lambda k and vk. Okay, so that's nice. The matrix here is always the same, which is nice because you can reuse it. It's non-singular. I mean, it's sort of an exercise for undergraduate students. It's V0 is in the kernel of lambda 0 minus A0, so this is a non-singular matrix, so it's invertible. We're all safe by solving this. There's obviously error, which I get to a bit later. So if you solve this system, say you can use a direct method, for example, and solve this, then the error accumulates, right? Because if you did an error here to get lambda 1 V1, it's put in the right-hand side. So there's an error accumulation happening. But let's talk about the positives first. So I said already E is non-singular. If you have an efficient solver for A0, say A0 is sparse, you can use a sparse direct solver. You can use some form of block ablumation with refinement, which is something that's been popularized by Govertz and Price, 1990, so it's relatively old. And you can solve the bordered system relatively efficiently. And yeah, the structure of E is essentially the same as the structure of A0. It's just some vectors added, yeah?
So when you say E is non-singular, we're assuming that lambda 0 is eigenvalue of multiplicity 1 of A0? Or something?
Yes,
okay.
That's true. Yeah, lambda 0 is an eigenvalue of multiplicity 1, yeah. Yeah, good point. And V0 is the corresponding eigenvector.
V0 is also simple, right? To begin with.
Say again?
V0 is also a simple eigenvalue.
Mu0 is the parameter. Yeah, mu0 is this is the point where you take a Taylor series expansion about. Yeah. Lambda 0 is a simple eigenvalue. Yeah. Okay. There's a couple of more things I wanted to say about the solver. As I said, I'm a numerical analyst. So if you solve this eigenvalue problem, you say you need all the eigenvalues and eigenvectors, so you solve it fully, right? You solve for all the eigenvalues and eigenvector. You can do this by usually computing the Shor form. So Q, there's a typo. Q, T, Q Hermitian. Q is a unitary matrix. T is an upper triangular matrix. In general, for symmetric problems, it's a diagonal matrix. It can be done in order n cubed flops, and that's basically the most expensive thing that you have to do, because you do that once at the beginning. And then you can reuse that, because I can write this matrix E in terms of the Shor form, because we can use the Shor form for A0, and the only thing that's changing here, then this 2-2 block, essentially, is a triangular matrix. And here you just multiply, pre and post multiply by Q, or Q Hermitian. So that's just a simple operation, and then what you basically have to do a solve with E is, E hat is a permutation of an upper triangular matrix, so that's easy solve, n squared, back substitution, or forward substitution, depending on how you order it, but here it's back substitution. And then you pre and post multiply with Q Hermitian as well. So it's relatively easy. That's n squared flop. So we've already done the expensive bit here. There's a Hermitian missing, as I said. So everything else can be done in n squared, or For the p term, you need p-squared matrix vector products. For the p is the number of Taylor series expansion terms that you use, so which is usually smaller than n. So that shouldn't be that much work. So your total cost is essentially your Taylor series, your Shor decomposition, and then some extra term. These extra term, if you compute one eigenvalue, there's an n cubed if you do this for all the eigenvalues here. So there's an order n cubed if you want to compute all the eigenvalues, which we want to do. We do this once, and then you have a nice parametric form of your eigenvalues and eigenvectors, which you can use for any of your algorithms that you would like to use. Solving an inverse problem, sampling, whatever. I get to that a little bit later. Okay, and here's the algorithm again. I'm not expecting you to read this, but it's really relatively simple. You solve just one eigenvalue problem, then you do the Shor decomposition. That's actually not even done here, but you can do the decomposition. But I would do the Shor decomposition. That's what we always do, and then you do the iteration. Right, let's look at this example that we looked at before and see if the algorithm works for that. Okay, as I said, if the algorithm fails for that, then we probably have a problem. You've seen this picture before, and this is the picture that you get by doing a Taylor series expansion until the order 6. We do this about mu0. Mu0 is 0.2 here. I think it's just 0.02. This is where we do the Taylor series expansion, and this the eigenvalues are the red crosses. The Taylor series expansion is the blue line. There's a couple of things that you can see straight away. It works relatively well around mu0, which is what we expect, because we do a Taylor series expansion about mu0. It works also close to 0, but anywhere sort of below, above, well, 0.04, so outside this box, essentially, you get rubbish, right? The eigenvalues get really far away from what they should be, which is bad news, but this is what we probably should expect, because it's a Taylor series expansion, right? What I should note, the Taylor coefficients still satisfy this property. You cannot see this here. Satisfy this property that the eigenvalues add up to 8, which is interesting. And what is also nice, you recover the crossing here. So the crossing of the eigenvalues is fine to deal with. Okay. Let's look at the error, because you can't really see much here. So let's look at the error. For a different Taylor series expansion up to the 25th approximation, so this is as high as we get, because then we get actually error accumulation, because we also get towards machine precision. And what is plotted here, because it would be completely cluttered if I plotted all the eigenvalues, I only plot one eigenvalue, which is here the largest, and the error for that. So the error between the largest eigenvalue of the Taylor series expansion and the one that you would get if we did the eigenvalue computation of A of mu for a fixed value of mu. Essentially the difference between the red and the blue line for one eigenvalue. But the picture looks different for all the eigenvalues. So I'm not hiding anything by saying I'm using the largest one. What you basically see here in this picture, everything is nice in the vicinity of your of 0.02, which is the mu0 that we chose, which is good. Outside, it's relatively bad, but we can get to machine precision. So, yeah, it's basically what you can expect. And okay, it's basically the same plot again, but with a higher range here. What I wanted to mention exactly, this is why this plot is here. This is the computation in double precision. You get to the essentially to machine precision. If you do the computation in single precision, you get to 10 to the minus 8 accuracy. Okay, so yeah, some discussion. So I mentioned this already. So the computation of the Taylor coefficient for both lambda and for the eigenvalue and eigenvector requires all the previous coefficients, and there's a sort of error accumulation happening there, which is bad. And the accuracy is only good in a narrow interval near the expansion point. So we need something better. Let's look at the second point first. The second point first. What we can do, we use different expansion points, so just do Taylor series expansion about different expansion points, and then use Hermite interpolation to connect those. The main problem here, it gets very technical, and also matching the correct eigenvalues together is a problem. So we didn't look at this further. But what we did look at, we thought, okay, let's, Taylor series expansion is not so good. Chebyshev expansion works possibly well in an interval, or a larger interval than just around a point. Right, but let's look at the Taylor series expansion again, because it motivates what the problem looks like for Chebyshev expansion. So you've seen this slide before. What I wanted to point out is that you can write this problem, instead of writing this as a successive solves with a different right-hand side, you can also write this as a big triangular system, namely a system like that. So it might not be so quick to see, but maybe sort of have an idea. So these are the matrices you're trying to solve with, and they are essentially more or less appearing on the diagonal. These are the coefficients you're looking for, and the right-hand side now has a 1 on the top and zeros below. If you solve, this is for p equals 3, so because I've only got a finite number of space on the slide, so this is only up to the third Taylor coefficient. So then when you do this, it's mathematically totally equivalent, so you can write this system as this one big block. When you do this, it's nonlinear. It's a nonlinear block lower triangular system. So nonlinear because also you have the terms that you're looking for also appearing in the matrix. So V1 is appearing here, but it's also something that you're looking for. But if you use an iterative method if you use forward substitution to solve this, yeah, so forward substitution, then you essentially get the same algorithm that I've just derived. So you, so if you use if you use forward substitution starting up here, you get the same algorithm that I've just derived, and it removes the nonlinearity automatically because you have no nonlinearity in the first term. You've solved, then here you plug this in, you do the second one, right? This is mathematically the same as I did before, just written in this bigger problem. There's a reason I'm doing this because the Chebyshev expansion will look very much like this. But mathematically it's the same as what I did before. So there's actually no nonlinearity. It just looks like there's a nonlinearity. But if you do the forward substitution, there's no nonlinearity. Okay, Chebyshev expansion. So I'm using, as I said, Taylor series expansion only works well around a single point. We want something that works better in an interval. The reason why we want to do this is basically when we use something like Markov chain Monte Carlo, you usually have a prior distribution. It could be the prior is sort of Gaussian, and it's good to look around a single point, and it's fine. But if you have a uniform distribution initially, then you want some interval where you want to have the eigenvalues estimated correctly. Okay, Taylor series, not Taylor series, Chebyshev polynomials of, here I'm using the second kind. And I need to scale them to the interval that I'm looking for the parameters that I'm looking for in a certain interval. You've seen this before, and this is the familiar recurrence for the Taylor polynomials. They are orthogonal. From this, you can actually see this identity. So if 2 mu is u1, it's 2 mu. So if I write u1 here, I get uk u1. Take this to the other side, I get this sum. And you might know, so this says almost any textbook, you might know that this holds. So if you have the nth Chebyshev polynomial and multiply by the nth Chebyshev polynomial, you can write this as this sum. There are students here who have not seen this before. I thought maybe I'd do a quick proof. I don't know what the time is. Maybe I shouldn't do a quick proof. But it's actually it's very easy to show, right? If n is equal to 1, n is equal to 0, you get u0. u0 is 1, is straightforward because only one term in the sum. If n is equal to 1, you put in u1. u1 was, you can use from the previous, from this formula here, u1 is 2 mu. Hang on. Yeah, you can use just this formula, uk times u1. So we have this already. u2, you then plug in, and you do some computations. Maybe I shouldn't do this here, but you can show this formula. If you're bored for the rest of the talk, you can show this formula relatively easily. So, and I'm going to use this later on. Okay, so what we do the same as for the Taylor polynomials. We just compare coefficients. Do a Chebyshev expansion of A, of our matrix, depending on mu. We assume there's a Chebyshev expansion of V and lambda as well. To get these coefficients here, we need to solve this integral equation. So we compute these AIs, and well, we use this formula. Actually, what we do in practice, we use Chebfun in MATLAB. So get these coefficients A0, A1, etc. Okay, so this is a bit more complicated than for Taylor series expansion, but it's doable. Okay, if we assume that we only look at the first term in the sum when we multiply um with un. So evaluating, comparing these coefficients now gets a little bit more involved because you've got lots of mixes of u0, u1, etc., right? So if well, some of those will be 0, but I'm assuming that um and un. This formula is used, but I'm assuming that only the first term really appears. So if I do that, I get a system like this, which looks very much like the system that we had for Taylor series expansion, and we can use forward substitution, but it doesn't give very good solutions. If we use the full sum here, we get a relatively complicated system, which is no longer lower triangular, so we can't use forward substitution. Yeah, we get all these extra terms in here. The color coding is basically showing you there's a lot of repetition, so this block looks like this block looks like this block, but there's a nonlinearity in here which we can't remove because it's not lower triangular, right? There's a dependency on V1, the right-hand side depends on V1 lambda 1, so this is a nonlinear system, and we can't remove the nonlinearity. So we have to use Newton's method to solve this. Newton's method comes with a lot of problems. We know that the initial guess is important, etc. But for the initial guess, I can say we can use what we get from here, from this system. Okay, so let's check what happens for the example, for this simple example with the exponential, Hadamard exponential and the Euclidean distances. So the example that I said, if it doesn't work here, and we're in trouble. So this is the first iteration. We are in an interval until 0.05, same interval we looked at as for Taylor series expansion. We look at the errors. So you can see these error plots. 1 Newton, iteration 2, 3, 4. So you're doing pretty well. And you see after, I don't know how far we go, to 8 Newton steps, we get close to machine precision. And this time we actually get good evaluation in an interval. So if you remember for Taylor series expansion, we were only good around, if the expansion point was 0.05, we were good here. Here we get a range between, say, 0.05 and 0.1, where we're good. And this is where we do the Chebyshev expansion about. Right? So we get good approximations in an interval. If we have a good starting point for the Newton iteration, convergence in new steps, but the convergence is not guaranteed. So that's sort of the bad news. But if you have a good starting guess, and we use, say, what I said earlier, we use a sort of startup phase where we have a good starting guess, then this works relatively well. Okay, these were easy examples. Let's look at some more complicated examples. I think I should be almost done because I'm just showing some more examples. Jordan block, and the parameter is this is this point, the n first entry here, mu is the parameter. We can find all the eigenvalues for this problem, right? Because they're basically the nth unit roots. So lambda 1 up to lambda n is something here, plus minus 1, and then scaled by mu to the 1 over n. So the units roots of mu. Lying on the circle, essentially. Okay, what does this look like when we do Taylor series expansion? So you've got the 25th Taylor approximation, so pretty good Taylor approximation. And as you would guess, near the expansion points we are fine. I'm plotting the real and the imaginary part of lambda. But obviously we get rubbish near 0, and also on the other side near the expansion point. So, and near 0, we cannot do any expansion. So if we chose mu 0 to be 0, then there would be a singularity. We can't do this. So this method has limitations. Okay, Chebyshev approximation works a little bit better in a larger interval, right? I'm just going back and forth. You see, Chebyshev approximation works in a larger interval, but again, near 0, we cannot do this. So we really there are limitations to this method. Okay, let's look at another example, which is a mechanical system. Say, it's again a stiffness and mass system. We're assuming we don't know the mass of a passenger in the car. So it's a 1D mass system, and you basically have the 1D mass spring system, and we have these two mu's in the mass matrix, which we don't know. It's not much more complicated than the system that we looked at, that I considered initially. Yeah, this works very well. So for simple problems, this works very well. This is a 6 Taylor series expansion. This is the error. And this is the Chebyshev approximation. And you can see if I compare this, if I go back, Taylor series expansion about 0.8. The Chebyshev expansion works in a larger interval, as you would guess. Let's go back to our problem, can you hear the depth of a water? So we apply this algorithm to this problem. Here's the setup again. What does the damping matrix look like? There's a bit more on the setup. So the trajectory we use, the time-dependent trajectory, we've got 50 time steps with each time step size 1/10. The starting point is randomly computed. The noise is a normally distributed. And we do Chebyshev expansion up to degree 9 for this problem. So initially we do a Chebyshev expansion. We have an interval, 2, 4 is the interval where we look for the eigenvalues. Where we look for the parameter. I'm looking for the parameter. The parameter is between 2 and 4. So we set this up all before. So we do all the expensive bit before. For the inverse problem, which I didn't talk about at all, we use 15 equidistance spaced mu k initially, and then we update. Okay, and some fixed point iteration. So, but we have done all the expensive bits before, so we know all the eigenvalues depending on the parameter. So we can just access our Taylor polynomials, right? So these are the initial mu, then we update, we check these mu, we update, and then we do this a couple of times, and after a while we get a spike, and this happens to be 3.2. This is a spike, and this is actually the value we set mu to be initially. So, and there's a very little variance here, so we get a very, very good guess. very good guess of the parameters, a very good solution to the inverse problem. But it's a simple inverse problem, right? One parameter, there's not even more parameters, so that's something to consider. What if you have multi-parameter dependence? A final point I'd like to make, which is something on sampling. So you might say, okay, why don't we just compute all? We want to compute the distribution of, say, the eigenvalues and for different parameters. So we have a distribution of mu, and the question is very much like the PDE uncertainty quantification people for PDEs. What does the distribution of the eigenvalues look like? It's nonlinear, so it gets really messy. So if you have a distribution of mu, you could sample for mu, and then you could compute the eigenvalue, all the eigenvalues, and sample and have a distribution for the eigenvalues. So what you could do is just you solve the standard eigenvalue problem 10,000 times. So you've got 10,000 samples. So for our problem, I'm doing this with 10,000 samples. So I'm choosing 10,000 samples, n is equal to 8, so you can still do everything, right? Solving 10,000 eigenvalue problems of size 8, you know, doable, easily. And I'm comparing this with what if we do the Chebyshev approximation or the Taylor series approximation first, so solve the expensive eigenvalue problem once and then use and compute the eigenvalues from there. For these simple problems, the timings will be very, very small, but the comparison is important. I'm choosing mu to be normally bit distributed and around 0.2, and I want to compute samples, lambda mu. And there's a big table, which I probably have to explain what's going on there. So the setup of the problem is in the first line. So how long does it take to compute these Taylor approximation and Chebyshev approximation for the small problem, right? So the coefficients, etc. This is the theoretical cost. This is the timing, the MATLAB timings for this. So the Taylor approximation is a little bit easier than the Chebyshev approximation as expected. The sampling is there's no sampling in the setup. So these are the setup costs. Then the runtime for sampling, if we didn't do this Taylor series approximation, we just computed all the eigenvalues and eigenvectors for all the different mu's, for all the 10,000 mu's. We solve 8 by 8 eigenvalue problems. It's 1.6 seconds. Not very much, because these are small problems, right? But imagine we wanted to do this for bigger eigenvalue problems. So this is what the sampling costs. And then what does it cost to just evaluate the Taylor coefficients, which we did that setup for the Taylor and Chebyshev. So how much does that cost? It's 0.08 seconds, 0.06 seconds. So if you compare this with this number, you get it's 20 times faster or 26 times faster. But then you might say, okay, we should also take into account the setup costs. So I'm adding these two numbers, 0.0096 and 0.096, which I get to this. So then the speed up is a little bit less. And here the same. I should include the setup costs, obviously, not to cheat. So you get 0.14, 0.06, you got 0.20 seconds. So the speed up is a little less compared to the sampling. This is for a very small problem, but it sort of shows this is better than sampling for all the different coefficients. There's something in this slide I should have removed. There's something Rayleigh quotient I didn't talk about at all, and it's good I didn't talk about this because I'm out of time. If you want to know about this, look up the paper or ask me. Just a conclusion, we've done Taylor series expansion to solve this eigenvalue problem. Works very well for small intervals. We've done Chebyshev expansion, works much better for larger intervals. It's advisable to do this if you do some sort of Markov chain Monte Carlo methods or something. And both methods work well if a large number of samples are used or needed, which is often the case in, say, Bayesian inverse problems. You need to sample a lot. If you are interested in the details, there is a PUM paper which talks about can you hear the depth of the water, And there's a preprint on Archive which talks about the actual algorithm for the parametric eigenvalue problem. And with that, thank you very much for your attention. Do I have to switch this one off? No.
I have to wait for that to go. It's gone green, yes. Thank you very much, Melina, for that very nice talk. Are there any questions?
Simon.
Simon.
Thank you very much, Melina. Your example 2, you had a singularity in the dependence on mu at mu equals 0. I think it was mu to the 1 over n or something.
Yeah. The Jordan block, yeah.
Perhaps you could comment on possible singularities and whether there are methods for dealing with those, or?
We haven't looked into that yet. We know there's a problem at singularities, so this is something we have to, future work, have to start working on, yeah. Yeah, these methods don't work for singularities. Yes. But for symmetric problems, we are safe because we don't have these singularities. It's usually Jordan blocks and defectiveness where this doesn't work. So you have to do something about that. Yeah. But happy to talk to anybody who has any ideas how to get around.
So I have one question. I couldn't understand your model. Somehow the masses in the water, are they the same as outside?
For this, yeah. For this,
but they should be lower because effective mass in the water is the mass of this thing minus the mass of the water inside.
You could set them lower. It's just for the setup.
So it should be smaller.
Yeah. You could do that. I mean, it's really just it's a very simplified model. We have the damping in the water, which we.
Yeah, but if they are made from metal, then the difference in damping is negligible.
Okay.
The difference in the masses is.
You could also put the parameters in the masses, as I did for this example with the car.
Yeah, thank you for a very nice talk. In the example with the Taylor series up to the sixth term, you know that the system is positive semi-definite, but then you get negative eigenvalues, right? Have you looked at methods where maybe you can preserve the positive semi-definiteness?
We haven't, but this is where we can probably have to go. So do some sort of constraint, add an additional constraint so that the positive definite is preserved. There are some things preserved. The sum of the eigenvalues is still 8 or n in this case. So,
okay.
Which is preserved, but not. Yeah, the Taylor series, the coefficients are going down. I mean, what we should do is probably do Taylor series expansion about several points, but that gets very technical. Yeah.
Okay, thank you.
Okay, I think one last question then. I think we have to wrap it up.
Thanks. We discussed already that the Taylor series expansion, at least as you presented it, works only for simple eigenvalues, right? Is there a way around that, or is it just to say, well, usually eigenvalues are simple?
We assume everything is simple, but for if your eigenvalues are not simple, you would have to use Chebyshev expansion, for example, or other expansions.
But in your example, you had a crossing, so there is a double eigenvalue, right?
Yes, but yeah, the algorithm still works. So even if you have, I mean, I have actually some more slides on, but I didn't want to go into them. So if you, it's known if you have. If a matrix is symmetric, for example, then the singularities are maximum algebraic singularities, and that maximum number of singularities are algebraic, and then you don't have a problem. Yeah. So there's a little bit of theory I didn't get into.
Okay, I think we'll have to wrap it up at this stage to stay within an epsilon neighborhood of the official timetable. So thank you very much again, Melina, for a very nice talk. Thank you.